Okay. Good morning. This is Gary Moyer. I'm the moderator for this session this morning, taking the glider from design to flight by Timothy Marinone and an introduction by Matt. And so we'll get into that in just a moment. First things up, this is one of the programs that we have on the technical committee, and we try to use both the full range of the American Institute of Aeronautics and Astronautics points of interest, including aircraft and spacecraft and space missions, mission systems, and any other area of interest that we can have. So today we have Tim Marinone, who is involved in the development of the Berlin glider, a glider that set a world record for altitude in unpowered flight, and particularly one of the main themes that he's going to be talking about is the flutter analysis. For those of us that are aerodynamicists or aeronautically trained, that's a particularly interesting subject because it involves all aspects of an aircraft's performance and the environment that you're in. And so Tim was involved in the initial testing and data analysis and revisions and modifications of the aircraft to fully expand its flight envelope. So he will also have a little bit of introduction from his employer, ATA Engineering, that is a service organization that is, well, they'll describe its full functions. I did have an occasion to work with ATA some years ago, and they're a very skillful, very experienced group of people. So Tim received a master's degree at the University of Massachusetts in Lowell, and he's been working about 10 years at ATA. He's basically a service engineer in addition to being a test engineer, meaning that he supports the functions that the Siemens Corporation's analytical systems carry. And that's a full range of equipment targeting from small corporations such as my own, which is a consulting company, to the major aircraft industry companies. So Tim is going to carry on with this in a moment, but first we'll hear from Matt Schumann.
Yeah, good morning, good afternoon. Morning to most of you folks in the Pacific West Coast. I'm up here in Minneapolis, so I'm central, just after the noon hour. So thanks, Gary, for that warm welcome. I appreciate it. I was just going to give another brief intro to ATA and our relationship with Siemens on this, the testing hardware and software side that can support projects like this, like you mentioned, Gary, on consulting and smaller company startup all the way up to majors like Northrop and Boeing and Raytheon and ATK and companies like this. So again, good morning and good afternoon. Thank you for having us today. My name is Matt Schumann. I'm one of ATA's business development managers, focused specifically within our dynamic testing group. We're excited to share with you the Berlin glider project that ATA Engineering was chosen to partner with on taking their world-class glider. Sorry, bear with me. I just lost my screen for a second.
Yeah, you're in the who we are screen with the with the staff photograph.
Yeah. Okay. Sorry. Yep. So housekeeping notes this morning. I'm not sure if we can have questions throughout because we have a small group. I think that's probably fine. I know previously we kind of muted folks out and then table questions. I can jot questions down or we can put them in the chat Q&A, but I presume we can kind of have it open flow if that's okay with Tim throughout. So Tim, if you want to go to slide 2.
Sorry.
So for those who are not familiar with ATA Engineering, we are an employee-owned small business with just under 200 full-time employees. Our staff consisting of many highly experienced engineers, project managers, and business development professionals who combine decades of industry and academic experience and achievement from undergraduate up to many with PhD level expertise. ATA's roots are deep into aerospace and defense, space exploration, and launch vehicles. And we also work with companies who provide fun things like themed entertainment rides and support manufacturers of heavy and industrial equipment, automotive and transportation. Our founders began many as aerospace and mechanical engineers, passionate about solving our world's most complex engineering feats. We have a large professional engineering staff dedicated to structural, modal, thermal, and advanced testing, simulation, and analysis. ATA Engineering has placed office locations from the West Coast to the East Coast, predominantly in strategic R&D locations to support aerospace and defense companies. We're also proud to serve as a platinum level reseller and a partner of Siemens going on more than 15 years. So ATA has developed some of its own proprietary software suite to support our customers, and we are one of Siemens' largest software solution integrators for engineering tools such as NX, Nastran, CFD simulations such as Star CCM Plus, SimCenter, which consists of SimCenter Test, SimCenter 3D, SimCenter Flow EFD, Teamcenter for PLM, and Solid Edge for CAD modeling. We support end-to-end engineering from training, service, license renewal, and new license and hardware sales. If anybody has any questions related to that, feel free to send Tim or I an email or call anytime. We'd be happy to help chat with you more about that. So Mr. Marinone is a project engineer, as Gary mentioned, with ATA's Advanced Test Group for more than 10 years now. Tim has supported customers with a focus on vibration and modal testing of defense systems and flight vehicles, and has performed real-time flutter monitoring of flight tests for military and commercial aircraft to ensure both flight safety and accurate flight measurements. Tim received his bachelor's and master's in mechanical engineering from the University of Massachusetts Lowell in 2010 and 2012, respectively. So with that, I'll turn it over to Tim, and he can share with you guys a bit more about the Perline glider story and how ATA took the glider to flight. Thanks.
Thanks, Matt. Thanks, Gary. Thanks, Ken. And thanks all of you who are joined. So as Matt mentioned, my name is Tim Marinone, and I am a test engineer at ATA Engineering. I also support ATA's VAR business as an applications engineer for SimCenter Test. So before we get into the specifics of the Perlin 2 project, I just want to sort of go over the agenda for today's talk. I'm going to start by spending just a few minutes with an overview of Flutter. I'm assuming probably most of you are pretty familiar with this, but just because I don't know the demographics, figured just a recap would be good. I'm then going to briefly talk about how the Siemens portfolio can be used at every step along the path as you go through that journey. And then I'll spend the majority of our time actually getting into the Perlin 2 glider and basically talk about how we help the customer progress from the design of the glider all the way through flight. And obviously this could be a pretty intensive and far-ranging discussion. So as a disclaimer, it's not going to be a Flutter course. It's not going to be a detailed dive into the mechanics of calculating Flutter. It's not going to be detailed dive into how to do a ground vibration test, model correlation, or flight testing. So if any of those topics are of interest, I've just provided a couple links to other webinars. One is another webinar that ATA did in 2021 that covers Flutter predictions analysis in far greater detail. with regards to using SimCenter 3D and Nastran. And so I'll do the plug. You can go to AT Engineering's YouTube page and find it there. And then Siemens also provides a lot of free resources. There's an article about ground vibration testing and flutter analysis. And there's also a free on-demand webinar about flutter clearance. So I just want to say there are some free available resources if you want to go a little bit deeper into any one of these areas. So as I mentioned, let's just take a couple of minutes to go over Flutter. I'm going to try and stay high level. So what is Flutter? What do we mean when we talk about Flutter? Well, we're talking about this aeroelastic phenomenon that causes a structure to be self-excited and extract energy from the airstream during flight. So this is caused by this complex interaction between three different sets of forces. We've got our inertia forces, our aerodynamic forces, and our elastic forces. And so you've probably seen either these videos or similar videos if you've been in the Flutter structural dynamics discipline at all. But basically what you're seeing is very visible movement of the wings. And so what's happening is that at certain combinations of airspeed and altitude, this dynamic pressure that the aircraft's experiencing can actually cause your frequencies of the aircraft and its modes to shift. And if the mode shifts in such a way that it couples with another mode unstably, then you're going to get this negative damping. Especially if it's a surface coupling, such as a wing or a tail, and it's like a bending or a torsion mode, then your flutter is going to really be a problem. And so I'm seeing a couple chats. I just want to make sure. Oh, okay, good. So the figure on the right shows an example plot of frequency and damping versus airspeed. And so what you'll see is that as we start to shift between 200 and 280 knots, these two modes shift to be on top of each other, and the damping of the mode in green goes positive, or what we call negative damping. And so basically it's saying at that airspeed, there is a risk of this flutter to occur. So why do we perform an aeroelastic analysis? So fundamentally, it's to ensure safety in flight. So you may have seen this video as well. This is a famous one from NASA. But as you can see, if the flutter conditions become severe enough, you can actually have catastrophic failure. And so you can actually see it damaged and ultimately get destroyed. And the challenging thing with flutter is because flutter is such a quick phenomenon that can occur, there's very little time to recover in the event that the pilot does start experiencing flutter. It's often on the order of seconds. And so it's really important to know when is flutter going to occur and to sort of safely stay away from those conditions so that you never get into a flutter phenomenon. So how do we do this? So at a high level, we're going to start with the finite element model or a simulation model, which we're going to use to calculate the aircraft's natural frequencies and mode shapes. And as we'll show when we get to the Perlin glider, we do need to have that confidence that our simulation model accurately represents our aircraft. So to do this, we perform what's called a ground vibration test, or a GVT, which is then used to experimentally measure the aircraft's modal parameters. Once we have experimental data, we're then going to compare it to our simulation, and we're going to perform a correlation updating process to reduce areas of uncertainty in our model and ultimately better match our actual hardware. Once we're confident in our model, we're then going to do an aeroelastic analysis to identify the flight regions where flutter is expected to occur. And then finally, we're going to verify that analysis by actually doing flight testing and actually measuring our frequencies and damping, measuring those aeroelastic properties, and confirming our analysis. So this sketch illustrates sort of the different steps in the verification process that's going to be typically followed by really anyone who's starting from either a clean sheet aircraft design or they're doing a significant mod to it. So you're going to start by having your FE model that you create, and then you'll do that ground vibration test that's going to basically validate that model. you might simultaneously also do a wind tunnel test and to validate the aerodynamics. Once you've got that, you're then going to typically also figure out, okay, how are you controlling your aircraft? And so that's when you go into the Ironbird and basically ensure that your control schema is not going to cause you to go unstable. And then finally, you take all those different pieces together and do your final air elastic models, and you do that flight flutter test. And so if you're familiar or if you've ever had to go through this with either FAA, ESA, or any of the other, what you call it, the compliance people, for lack of a better word, basically they mandate you go through this process to show that you're going to be flutter through your entire flight envelope plus an additional safety margin. And so it's really important throughout this whole process to have really good data so that you have confidence before you go to your flight flutter test. So I do just want to take a moment to go over the Siemens portfolio. So as Matt did mention, we are a value-added reseller for Siemens. And so just want to briefly talk about what they offer if that's of interest to you. So the first thing we're going to do is go back to that initial high-level view of the interactions between the three forces, our inertial forces, our aerodynamic, and our elastic. And so our governing equation is that the aerodynamic forces that act upon the aircraft, meaning F of t, are going to be balanced by those inertial forces, our mass times acceleration, and our elastic forces, our stiffness and displacement. So how do we get those interaction of those forces? So the first thing we're going to do is we're going to do our interaction between our inertial and our elastic forces, which is our structural dynamic portion. So for this portion, we'll do our modeling and modal analysis in SimCenter 3D using structural dynamics. And then we'll do our testing with our GVT using SimCenter Test Lab. And so we'll talk about that a little bit more on the next slide. So next is our interaction between our inertial and our aerodynamic forces. So for this portion, we'll do our CFD analysis using SimCenter Star CCM. And then we'll validate that model with the wind tunnel test. And so lastly is our interaction between our inertial and our aerodynamic forces. Sorry, interaction between our elastic and aerodynamic forces. And so in this case, we're going to do a static aeroelastic analysis using SimCenter 3D and SimCenter Nastran using solution 144. So once we've gotten all those different pieces together, we can finally do our flutter analysis. So if we're in a subsonic regime, then we're going to be able to use SimCenter 3D and SimCenter Nastran with the solution 145. If we're in a transonic or supersonic regime, then we'll have to use SimCenter Star CCM and SimCenter Nastran. So what I hope I've showed you with the slide is just, this is a very complex problem, as I'm sure you're aware, but Siemens does have the portfolio to handle it. Oops. So SimCenter does offer a complete streamlined solution to characterize the dynamic behavior of a structure, both numerically as well as experimentally. So kind of the way this portion works is you start with doing your pretest analysis. So you're going to have an original model. It's not yet validated. And you're going to use that to sort of decide how do you want to run your test. So where do I want to install my sensors? How do I want to excite my structure? And so Test Lab and SCADAS are then going to allow you to actually perform the test. And so you're going to do your instrumentation, your measuring, and then your modal analysis so that you can get efficiently reliable FRFs and get that best experimental modal model that represents your data. Once you've got your set of mode shapes, your experimental results, well, then you're going to take it and go into SimCenter 3D and the structural dynamics and actually compare your model to your test data and do any correlation updating in order to better match your model to your test data. And then finally, from that point, you can then go into your flutter simulation. And then I just wanted to go for anyone who is in the flight testing world. Siemens also has a solution for as you're going through the flutter testing campaign. But also, if anyone has never done flutter testing, it's really instructive to kind of see how it goes. So what we have here is a nominal set of flutter test points that we were intending to evaluate. So this initial dashed line is sort of the initial clearance that we're allowed to fly. And then we're trying to get all the way to that, that larger line. And so at each test point, what we're going to do is first we're going to go to that first test point and we're going to get our aircraft there. And so it's a certain combination of airspeed, it's a certain combination and altitude. At that point, we're going to activate our flutter excitation system and we're going to collect that data. That we're typically going to use telemetry data and send it to SimCenter Test Lab. Because it's really hard to actually stay perfectly at altitude and at airspeed, and we're going to expect to see some variation. We're going to average those flight parameters to get sort of, okay, what is our average flight test point? At that point, we're then going to automate our modal analysis, our operational modal analysis, and we're going to extract frequencies and damping that we're seeing from our aircraft. And so from what that allows us to do is that allows us to track our frequency and damping with respect to flight conditions and identify, okay, are we at the point where we need to start, we're getting really close to our flutter to zero damping. We need to be very careful, or no, we're still very well damped. We can just go to the next point. Typically, you're going to have your flight test engineer that's overseeing. They'll look at the data, make sure everything looks good. And then if everything looks good, you get cleared to the next point, tell the pilot to go to that next point and then repeat. And so over time, that's going to give you your, allow you to expand the flight envelope. So with that being said, let's get into the actual discussion of the Perlin 2 glider. And so I know that Jim Payne from the Perlin project did present, I think it was a couple years ago at this point. So this will be coming from a little bit different perspective than what he presented. But just to recap, for those of you who either didn't see that talk or have forgotten, so the Perlin 2 is a composite sailplane designed to fly to 90,000 feet. ATA was not involved in the previous iteration, the Perlin 1 design, but it set a record in 2006 for powerless flight at just about 50,000 feet. At that point, they realized, okay, the Perlin 1 design was not going to allow us to go much beyond that. And so they did this redesign in order to get to the Perlin 2. And so as of 2018, it does have a world record of 76,000 feet. Still can't go up to, haven't made it to 90,000 feet yet, but they're hopeful. And so why that's interesting is because of the way that the Perlin 2 actually works. And so because the Perlin 2 is a glider, it doesn't have any engines. And so how does it hit this altitude? So what they found is that there's this phenomenon called stratospheric mountain waves. And basically at certain mountains, and it's really the Andes in Peru, you basically get this actual wave that comes off the mountain. And so I don't fully understand all the meteorological phenomena that causes it, but what it allows them to do is basically ride those waves, and depending on what the wind is, what the temperature, they can actually get very high. So in order to get to that initial part, what they do is they actually get towed up to that minimum altitude, and then from there, they'll surf it. As you can imagine, they're trying to hit that goal of 90,000 feet. There's significant challenges due to both the air density and the temperature. And so there was a lot of engineering design that went into how do they actually make sure that it's still going to function at both sea level and at 90,000 feet. However, before we get into that project, I would like to show you the video that they put together in celebration of the record. So hopefully this will work. It's always fun showing videos, but let me know if it doesn't. 1 second. Let me stop sharing and try this again. I apologize for this. Let me just pull it up online real quick. Alrighty, look back to that. And this. And this. Okay. And make that full screen. Okay. Hopefully you can hear this now.
Yep.
Our goal is to fly to incredible altitudes in the stratosphere.
We need very special conditions to fly into the stratosphere. Yes, this glider does actually do what we designed it to do.
The dream was born for Parallon Mission 2. A lot of individuals got involved to make that dream a reality.
We've come to El Calafate in Argentina.
Our goal is to get into some rising air.
We're looking for areas of lift that will enable this aircraft to get into the upper reaches of the atmosphere.
And there's only a few places on Earth that have stratospheric waves.
We can put the glider into a patch of air that is going up at incredible speed, 1,000 feet per minute. You know, the same kind of speed you're climbing when you're in an Airbus airliner. We're going up at that speed, and it's actually nice to fly.
The virtual cockpit gives us all the information on the ground that we need to know if the flight is progressing safely and smoothly, and that we're able to continue to progress higher and higher.
We've added even more to the virtual cockpit. So this year we have a live video feed from the tail camera, which should immerse the user even more into the flight experience of Perlan.
We look at the pressure in the cockpit, in the capsule. We look at oxygen that the pilots are breathing. We're looking at the battery. We're looking at temperatures at various instruments.
If you want to be an innovative company, you have to be doing things that nobody else is doing, trying things nobody else is trying, and doing them in a way nobody has done them before.
Perlan is an amazing opportunity that you don't get very often.
We worked with a small school that's trying to form hypotheses to get kids inspired in science technology.
Aviation is a fantastic potential career.
There is true adventure, true exploring here.
The perspectives you get from flying high, the freedom, the enjoyment have just been fantastic.
So yeah, I thought that was just a really cool video to kind of see the excitement that they've got. So let me go ahead and get back to the presentation. Okay, I think we're back in business. So basically we start by just creating that final element model. So yeah, as I mentioned, the Perlan 1 mission did set that record in 2006, but in order to achieve the new altitude performance as desired by that team, they had to do a significant redesign for the Perlan 2. So they started out with a computer model with solid geometry. And that's when they reached out to ATA and asked for help. So we took that solid geometry, we converted it into a finite element model. And of course, you would love for that to be seamless, but inevitably you find that there's issues. And so we immediately noticed that there's a significant missing amount of information in order, especially with the stiffness and mass. Lots of joints that were uncertain. And so you need to go, okay, how do I fill in that information? And then ultimately, because we're missing that information and we're making our best assumptions, now how do I make sure that my model is correct? And so we're going to do that by performing a test to get an accurate representation of that aircraft, especially in, like I said, in joints where you have that uncertainty. We also actually use the solid geometry to make sure that the glider would fit inside our test lab. So as you can see, we don't have a big hangar. We have a more of a small test lab. And so luckily, and I'll show you in a bit, the glider actually came into pieces, which allowed us to basically build it, assemble it inside our test lab. But you can actually see you've got the tail sticking out. You've actually got part of the wing sticking out. So we basically just managed to have it fit. And even then it was had a little bit sticking out. So like I said, that this was kind of interesting because most of the time when we're performing these tests, we're going to the customer site. As you can imagine, that people are generally not flying 747s or military aircraft down to our test lab to test. And so all of our equipment is designed to be portable to go to the company. But in this case, we were able to do it at our facility. And so they actually carried it in a big U-Haul with a trailer down from Oregon. And you can see we actually were unloading it, a very manual process to get everything off. And then, so the first thing we did obviously was to get mass and CG. So we wanted to make sure we weighed everything, all the major components, just to sort of make sure that we did understand if the as built masses were like the drawings. And so from there, we were actually assembling it onto the fuselage. At that point, we installed accelerometers. And then we actually suspended it with bungees. And so that allows us to get this boundary condition that basically resembles what it would be in flight. And from there, we can use shakers to excite the aircraft and to get measurements. All right, I'm going to assume that this is also, oh, here we go. Oh, sorry about that. So, and what I thought was really interesting about that is, especially for people who are typically don't see this a lot, or maybe they only get to see it like once or twice in their life. It's really interesting just to kind of see how this type of test progresses, and you can see even with it sped up the way it was, there's a lot of instrumentation, there's a lot of work that to be done, and that this was a not a huge test in comparison to some of the others we did, but still a pretty significant effort. So once we'd done the test, we got all of our data. We were happy with our final set of results. We then wanted to go back into our model and update our FEM. So we first focused on the mass and CG of the individual components. Since we had measured directly, and we had a lot more confidence. And so you could do that by adjusting the density, by figuring out any non-structural mass of the elements in order to match that test data. We then focused on the stiffness properties by adjusting both material properties as well as the joint spring properties. That allowed us to better match the test data, to better match those mode shapes and frequencies. And so at the end of it, we had a correlated model that we were happy with. So once we'd gone through that correlation process, we were ready to create our air elastic model. So this was Perlen's nominal design dive speed envelope. And so you can see that they have that 90,000 feet on the top, and then they had the different Mach values that they were targeting. And you can see the blue was their goal that they wanted to expand to. So we wanted to determine if that whole flight envelope was usable. So to do that analysis, the FEM geometry was used in order to develop that air elastic model. So in the air elastic model, you use some simplifications. If you have a lifting surface, you're going to model it as a plate. So that was the wings, the horizontal stabilizer, and the vertical stabilizer. And then if you have a non-lifting surface, like the fuselage, you're just going to model it as a simple body. So when we did the initial flutter analysis, we did see that there were some modes, some instabilities that were likely to occur during flight at some combination of airspeed and altitude. And so we wanted to be like, okay, let's make sure that these are the ones we're going to be tracking. Before we even got to flight, as part of the correlation effort, we noticed that the aileron, and as you can imagine with the Perlen, there are multiple ailerons because of the length of the wings. It was really sensitive, and that if we were able to increase that aileron torsional stiffness, we would have significantly better flutter predictions. So we were able to do that, and that did help it out a lot. But obviously, we still wanted to do that flight testing in order to validate the analysis. So if you've never been done flight testing is always a challenge because you're basically trying to run everything off of aircraft power. It's really challenging to get sensors on the aircraft, and so, excuse me, and then especially for Perlen team, which doesn't have the resources and the budget of, say, a large airplane manufacturer, they had to be very creative. And so they actually created this custom data acquisition system where they used an Arduino board for the actual acquisition, just a basic 3-axis MEMS DC accelerometer, and then stepper motors with offset masses. And so you can see in this picture on the right, we were comparing our reference accelerometer, which is a much higher performance accelerometer, with theirs, just to make sure that it was seeing the same results. And then in this other picture, you can see that we were actually running the stepper motor. And so you see the mass at the bottom, and as it rotated, you would measure with the force, and we'd be able to figure out the maximum force that the motors could impart to the aircraft. But this was just a really nice, clever way to do this type of work. So at the end of testing, Perlin was ready to fly. So data from Perlin was sent to ATA, where we processed the data and compared it to analytical predictions. One aspect that was interesting with the Perlin flight testing is that unlike a powered aircraft, where you can set the altitude and speed fairly precisely, the glider is obviously wholly dependent on the strength of the atmospheric waves for a given day. So a lot of these test points, you end up sort of hitting them over and over because those were the only points that they could hit if the waves weren't necessarily strong. Flight and flutter testing in particular, the data is rarely as clean and nice as you would hope for. However, ATA was still able to pull out results for the modes of interest. So you can see the frequencies for the 5 modes of interest. The lines are the predictions from our analytical model, and the dots are our test data. And yeah, the frequencies overall compare well to the predictions. The damping is a little bit more scattered, and that's because it is a lot harder to measure damping accurately. But overall, it did follow the general overall trend, which gave Perlin confidence to continue testing. So ultimately, the Perlin project is still ongoing as they attempt to hit 90,000 feet. As you saw in the video, they've also begun to focus more on scientific experiments. The area between 40 and 160,000 feet, known as the stratosphere, is really of particular interest to a lot of people as we're studying the Earth's climate. What is nice about the glider is that it is one of the few research aircraft that can stay in the stratosphere for a long period of time. So with that being said, I would like to thank the Perlin project team for their permission to publicly discuss their project. They've been remarkably willing to allow ATA to showcase this project for case studies for research. Hope I've given you an overview of Flutter, shown you how the Siemens portfolio can help you in the process, and walked you through the process of how we took the Perlin glider from design to flight. It was a really fun project to be involved with. At this point, I'd like to open it up for questions. Thank you.
Okay. If anybody would like to put in a chat in their questions, I meant to ask this before the presentation. If you could do that as you were watching the presentation, that would be best. But somebody raise their hands and see.
So what was that mode 9 that popped up so early, and why did it go away at 6,000 feet? Like at lower altitudes, it went away.
Yeah, where was that?
Right there.
Yeah, that was where mode 9 was the fuse lateral and the wing anti symmetric. And so yeah, what's interesting is that it's really only at the low altitude where your dynamic pressure is heavier where you see it. And then I think, let me go back to the data, mode 9, so that's blue. Yeah, you really don't start to see it as you sort of get higher and the damping goes way down. So basically, it kind of almost was no longer being excited at that higher altitude. Did I answer your question, or did I just talk around it?
Oh no, that's fine.
Okay. Okay.
So these modes that were of particular interest range from about 4 hertz to about 19.
Mm-hmm.
Okay, and as the dynamic pressure increased, the frequencies changed slightly.
Yep. Yeah, and so because we never got high enough to get to interesting from a aeroelastic point of view. You can see that as we would have gotten closer to that to the right side of the curve, you would start to see the damping trend back to 0. And you can see on the left with the frequencies, those 3 modes starting to get awfully close together. That would have been kind of the area of really interest, but we weren't able to hit those levels just because of the waves. And so that's still sort of an ongoing effort, but they've been focusing more on generally staying within their current envelope and doing more experiments and flying in the range that we've cleared them to.
And so the maximum dynamic pressure that you've achieved at this point in test data is around 0.0015.
Correct. Yep.
And I don't recall what the answer was with regards to what that corresponds to in Mach number and altitude, but
yeah, it was. Oh, I don't have that plot. But yeah, it's they got. I mean, ultimately it was the 70. Oh gosh, where is it? 75,000 feet or so. But yeah, the airspeed is pretty low at that. Oh, I went too far. Sorry. Yeah, 76,000. So I think it was pretty slow. I think maybe like 100 knots at that speed, but for that altitude. Yeah. Yep.
That's
yes.
indicated. But
correct.
But the true Mach number, the true true velocity relative to the surface,
right,
substantially higher than that.
Yep.
I have a question.
Oh,
Yeah.
Sorry.
And you are?
My name is Giuseppe Veneri, and I have a question about. Could you briefly describe how you average the raw data to get the modes? I forget exactly. I know there's like ways that you shouldn't do it, that you'd probably mask data, but how do you do it so you don't like lose critical information? Sure.
And you're talking about during the ground testing or the flight testing?
The flight.
Yeah. So the flight testing is definitely some of a let's see, probably this was probably the best slide to show it. Yeah. So what you're there is a little bit of art to it, but basically what you do is when you're flying, you're trying to excite a particular mode or set of modes. And so the stepper motors, you'll try and drive it at the frequency that of that mode because you want to ideally you want to drive energy just to that one mode as best as possible. And then what you can do is you can use you have a set of accelerometers, and so generally you'll do what's called spatial filtering, where you're either adding or subtracting combinations of accelerometers to really just focus on that one mode of interest. So if it's torsion, you're taking one from the other. If you're maybe doing symmetric bending, you're adding them. And ultimately trying to get the final set of measurements that you can then do your modal analysis and get your frequencies and damping.
Okay, so you are pretty much inducing the modes that you're looking for with the stepper motors.
Correct.
Okay, and so this test is done, say, first of all, are there 2 people on the Perlin 2?
Yeah, there's always a pilot and a co-pilot.
Okay, and is the test done, say, with 1 pilot, and then the real test is done with 2 pilots to offset like the weight of the instrumentation?
So let me think about it. So we actually did during the ground testing, we actually studied the configurations of 1 pilot in the front, 2 pilots, and tried to give like a nominal, okay, what if the pilot had a really big meal the night before, and tried to bound that problem. And it is, there was some effect just because of the fact that the glider is overall relatively lightweight, but it wasn't significant enough to dramatically shift the dynamic properties of the aircraft.
Okay. One question, in your analysis, did you find that, say, wing sectioning was ideal, or would you have like output like a different configuration to like sectioning the wings to help modes out?
Sorry, can you say that again?
So say the wing was divided into 3 or 4 parts. If you divided it into, say, less parts or more parts, was there like an output from your study that you said, like, if you did a 3rd version, maybe you should do this?
Oh, yeah. So you're talking about in the actual assembly?
Yeah.
Yeah. So what actually the way they have it, as you can see there, the main part of the wing is sectioned there. And then the picture is like just on the other side of this picture, but basically the main part of the wing was one section. And then it was actually just the winglet and the last couple feet that was a separate section. So in this case, it was just the 2 sections per wing. But no, I don't think we did any trade studies as to whether more or fewer sections were advantageous.
Okay, all right, that's it. Thank you.
Of course, the mass moments of inertia are very important in photo analysis, particularly on a long, thin wing like this. Curiosity about what the aspect ratio is, but
I forgot to
attempt to significantly change the mass moments of inertia by putting any ballast weights at any particular locations.
Yep. Yeah, that was a big study, was what sort of mass they needed to do with the control surfaces in order to make them more dynamically stable, to shift frequencies around. So there was a fair bit of trade studies involved with that. The nice thing was that those masses were on the orders of a couple pounds, so they didn't have to be huge. They just had to be located at the right locations. Yeah, I didn't write the aspect ratio down off the top of my head, but it's a total of, I think, 80 feet long, and I mean it's only 4 or 5 feet wide, so we're actually not even that. It was a high aspect ratio, but I don't have that number off the top of my head. It may be online.
I'm sure it is.
All right, I see we've got Q&A in here.
Okay.
Gary, I think George raised his hand.
Yes.
Okay.
This is George Chow. I have a fundamental question.
Okay.
What's the purpose or the applications flying a glider at a high altitude of 90,000 feet?
Sure. Yeah. So, I mean, obviously part of it is just to set a record, but the bigger part of it is that at the stratosphere, there's a lot of really interesting climate and sort of, we don't have a whole lot of information in this area of altitude. We really are good at our everything below 40,000 feet. I mean, we're flying there all the time. We have lots of measurements, but once you get above that level, it really drops significantly. And so you can do obviously balloons, you can do obviously powered aircraft, but then you've got really limited time duration you can spend there. And you also have all the effects due to the burning the engine. And so it's really hard to maybe get accurate measurements of temperature, of wind, et cetera, that you want to do. And so the glider was really designed to be able to take long segments of scientific data at those altitudes where we just don't have a lot, but where we're noticing that with a lot of these climate models, that's becoming an area of uncertainty.
I recently saw. Yeah, good.
What's the maximum flight time over there?
I mean, so they're in theory, their maximum flight time is just is really their battery and their oxygen. But obviously they can, as long as the waves are working, they can fly effectively forever. I think their longest actual flight's been a couple hours. But I think they've designed it to be, I want to say 7 or 8 hours of flight time that they could achieve if they were able to.
Okay, thank you.
As for the application of what stratospheric atmospheric data is concerned, the advent of hypersonics in the upper atmosphere is something that is very dependent upon the atmosphere. And we have very little actual data in that region. So Aviation Week recently made some comments about that.
Yeah, good point. I wasn't even thinking of it from that perspective, but yeah, that's even more interest in some of this data.
Yeah, the rockets get through that region rapidly, and there's experiments in that. But the duration and the geographic distribution, that's another matter.
We have any questions in the chat?
Okay, I see a Q&A. Did you significantly modify the size of the glider during the study? No. At that point, they had sort of already taken the glider 1 design, had sort of already converged onto the sort of the overall parameters that they wanted to do. So by the time we got to it, it was more or less, here's the overall design. You work within this box.
Okay. Let me interject an issue that might come up. I'm located in another library in Riverside, actually, and I may lose this room within a few minutes. In which case, I'll leave Ken to complete the remainder of the interviews. But otherwise, do we have another question?
Kind of related to aspect ratio, but what was the max L over D for the for the glider?
Oh gosh. I should know this. I do not have it off the top of my head. Let me
Is it above 50?
I believe so.
And do you know the actual weight, the design weights?
Oh, did we put it in there?
These things are amazingly light for the size.
Yeah, I don't think, I think the backup slides got taken out that had a lot more of this stuff.
Okay.
Yeah, let me,
Those envelope diagrams were particularly interesting for flying a straight wing aircraft at Mach 0.7. You're pretty much at the limits of that.
Yeah.
Oops, I've got my screen covered up with chats and stuff.
Okay.
So what is their strategy for hitting 90,000? Are they trying to go on a diet? Are they trying to get more speed? Or are they just hoping for better weather?
Yeah, I mean, it's. I think they've been, and I'll confess that obviously with the pandemic, they kind of put this on hiatus a little bit. Yeah, I think they are mostly focused on trying to get better waves. I think they're obviously looking to see, okay, what is there a way that we can take off? But they've done a pretty good job of optimizing. I think the 90,000 is as much a like, it would be really great to set it, but I don't know if there's the funding to do what would be needed to get there versus if you saw in the video, Airbus is sponsoring them. And so going, okay, hey, you still got the 75,000, but you've demonstrated the glider works. So yeah, I know they're obviously at everything is all money based, and so I haven't heard the latest as if they're attempting to come back to flight testing or if they're more just yeah, I don't know what the latest is.
Okay.
Yeah. Matt put something interesting into the chat here, and that's about the visual image correlation, which is an issue that we were looking at some years ago, because you know, extremely light structures like this are hard to instrument, and you need to be very careful about what the effect of the instrumentation is on the load shapes and other information.
Yeah,
mass properties particularly.
Yeah, guys, feel free to join us if you're interested. Tim is, I think, going to be one of the main presenters from ATA just with our project staff. But this is going to be a co-hosted seminar with Siemens on some pretty cool new high-speed cameras that they're offering. I believe it's a company called Match ID. And this is also a technology that's going to be coupled within ATA's advanced test group and the hardware and software offerings from Siemens and through ATA's of ours. So this should be a pretty exciting seminar. If you click that link, there's a detailed dive on each. There's going to be live demonstrations, a lot of work that went into it. It's a full day. So we'll have breakfast in the morning and coffee and lunch catered throughout. And it'll be in our Curiosity, our largest training room inside of ATA's corporate headquarters in San Diego.
Oh, that's actually going to be an in-person event, or is it also?
Yeah, that'll be in person.
In person. I don't think it's going to be recorded or broadcast via video feed. In person for this one.
Very interesting.
There's a question. Do you have some sort of a research paper out on this topic? I guess I'm not entirely sure what specifically. We obviously have approval to present a lot of their stuff, but they ultimately own all the data, and so this was about the extent that we were able to share. And it's this I would say nothing that, or I think this was just really interesting to sort of walk through because a lot of engineers get to see pieces but not the full thing. But I wouldn't say that there's anything that we did on this that was necessarily noteworthy or innovative enough that would be a research paper focus. But maybe if you had a specific question.
I think maybe do you have like on your website a link that you have your published paper on this posted publicly, or people have to purchase the paper or something?
I mean, so we do have I don't know if it's a white paper. It may just be like a case study that we've done online that we could pull together.
Yeah, that would be great. Then we can post it. People can learn more about your engineering effort.
Yeah.
Now, with this diagram right now, I just got around to reading the axes on it. And you said once that you're running close to 100 knots calibrated airspeed is at maximum. And I see that about 63,000 feet, that's right at Mach 0.7. That's closer to what I was previously asking about than I expected.
Yeah, and I may have been rounding up a little bit. I'd have to go back to the raw data, but yeah, it was. it was moving.
But do you know what the stall speed is?
Oh,
It must be it. Well, no, these are flutter limits. No, that's
right.
VD and VD plus 20%.
Mm-hmm.
So the VD is really an indication of what the maximum intended speed is.
Right.
Yep. And they were attempting to push that out to the right, weren't they?
Mm-hmm.
Any success on that?
I think sort of the same thing. They were, again, with unfortunately with the waves, it's in order to get the high speed, you actually have to get pretty high and then obviously dive down. And so initially they focused more on hitting the altitudes than the velocities. So I don't think we've gotten all the way to the VD part of the curve yet.
Mm-hmm. It'd be interesting to know where the minimum drag speed was in calibrated airspeed.
Right. Yeah, I can see if I can pull together. I know we have all that information, just not off the top of my head.
Sure.
Recording in progress.
So for the flight test,
mm-hmm.
When you were the exciters aerodynamic or inertial?
No, so they were you can see here. So they were inside, so inertial. Yeah, inertial.
Okay.
Yep. So it's basically just an offset mass that rotates.
And that's standard practice for air elasticity tests. You do not want to have the excitation from the aerodynamics when you're approaching the critical speeds.
Right.
So you want to excite the mode and the frequency as you approach the speed, and you see how the damping is coming out, and where you have to stop.
Yep.
No, I understand. We've used barrel testers in the past that are essentially just slotted cylinders that are, can generate more forces with less inertia. But like this, I was just wondering if it was too delicate to pull that off.
Yeah, it was. I mean, the force they were applying, I think, was only on the order of a couple pounds of force. So.
Yeah.
Mm-hmm. Well, you didn't have an exact number on those on the mass of it, or but of course the frequencies were essentially along the frequency of the mode. Mode shape there. So.
Yep. Yep. But yeah, it was a nice, relatively cheap approach to take.
How close to what kind of damping level were you willing to go down to?
So, I mean, we never, because of the fact that we never started to get to that curve, we had like a nominal, but it was sort of an arbitrary, we were kind of gonna, as we snuck up on it, started to have more in-depth conversation, and just never got to that point. But yeah, probably, I think it was something at 0.02, 0.03. But it was more looking, I think once we had hit that curve was when we were going to start being a lot more diligent, because the challenging part was that we were not real time, we were near real time, but ultimately the pilots had to have clearance to proceed without us, and so as opposed to like a lot what other flight testing we've done where we're in a control room and we're seeing the real-time traces and we're able to say knock it off abort as needed. This was more of okay, they're going to do the maneuver and it's going to take us 15-20 minutes to get the data to process, to tell them the values, so we had to be a little bit more conservative.
Now, interestingly, when you test a very light object such as this in an ordinary atmospheric environment, the masses and damping of the aerodynamics of the air load or the effective air mass on the plane becomes significant. Were you able to comment about that?
Yeah, there was a we didn't really go into that. Obviously, we tested at flight level and then just used our predictions to account for the altitude. Yeah, it would have been interesting to have done more. But yeah, it was obviously budget related. We can only do so much.
My ancient history was that when I was in school, I worked on in the Boeing wind tunnel model design, and one of the projects that I worked on was an aeroelastic wing of the SST. And I sometimes say that we actually won that proposal, and we lost the the DC, the C5A proposal. So I worked on both of those a little bit, and in the end, Lockheed was already flying supersonic, triple-sonic.
Yep.
And Boeing turned the C5A proposal into the 747. So interesting combination there.
Yeah.
Sometimes you win when you lose.
Sure.
Well, it's gotten, oops, wait a minute. A question, how important is aerodynamics for a structural engineer? I have a hard time understanding the depth of it, although I'm an aerostructures engineer. Any advice?
Oh, yeah, I mean, that's...
Depends on the size of the program.
Right, yeah. I was going to say, if and the size of your company, if you've got a big team, I mean, obviously, yeah, I'm always going to recommend you understand more than less, but yeah, if you're working with a dedicated aerodynamics or elastics group, it's probably not as important as long as you understand the high levels. But yeah, if you're working on a team of 2 to 5 people, you probably should know it pretty well.
It's always good for table stakes.
Yeah.
Oh.
Okay, Gary, I have a question.
Okay.
This Perlan 2 glider has been tested in Argentina, and you also mentioned it's very good for science study for stratosphere. Can this Perlan glider be applied? I mean, can it fly anywhere around the world? Just study the science atmosphere, any place in the world? It has to be, things like a mountain area, like the one in Argentina for the test. I remember Jim Payne mentioned something that there's a reason for doing the test over there. So would that be general enough that people will be interested in scientific study using Perlan? If it's just locally, then you are studying just a local atmosphere or phenomena. But I understand there's a reason for doing that, but can you comment on that?
Yeah. I mean, I guess I use the analogy of surfing. And so obviously you can surf multiple places in the world, but if you want to get the biggest waves and the most exciting, there's certain places where you're going to go to. And so this is very similar where, yeah, you can fly anywhere. I mean, obviously the glider doesn't care about that, but you have the challenge of if there's just not a lot of energy in the atmosphere at where you're flying, you're not going to be super successful, and you'll get towed up to your initial altitude, and then you'll be just doing a gradual descent the way you would with a normal glider. Whereas if you're in a place where you do have the mountains and you have the high stratospheric waves, well, now you can really ride that energy and get to higher altitudes. But yeah, I mean, fundamentally, there's no reason not to. Practically, it's not every place will be the same.
You need a set of mountains, and you need a desert on the backside of the prevailing winds from that mountain.
Right.
Like you see that. So it has to go in that order. And then, and if not, then you're right. It's just a glider.
But did you identify any place else in the world that you can have?
So we have Moriarty. Like, I mean, I've been out there. So like Moriarty, New Mexico,
great,
is essentially what we have, but it's not as cool as Chile. It's not quite as. And I'm sure there's some places in China. There's definitely some places in Africa, but everyone, I mean, everyone knows that this place is where you try for the big numbers.
As I'm looking at the image of the waveform after the mountains there, I'm reminded about a series of studies that a friend of ours, Phil Barnes, produced. And I don't know if you're familiar at all with Phil.
No.
Phil is an aerodynamicist, recently retired from Northrop Grumman. And he has a website that's identified as How Flies the Albatross. I guess I'll put that into the chat area here. So How Flies the Albatross is based upon his study of how does the albatross stay in the air for days and weeks at a time, practically without flapping its wings.
Right.
And it's basically a matter of climbing into the wind and descending in the valley. And they managed to put one side of their brain to sleep so they can do this continuously and still have some consciousness operationally.
Yeah.
And it's a very interesting presentation. It's available on his website, along with a number of other things that are interesting.
Yeah, no, I mean, it would be interesting to see if you could do fly-by field on a glider like this to have it, aerodynamically more responsive to the environment, both perceptive and, morphing wise, if they could go that little extra further. Like, cause I mean, that's, when we think about birds, we kind of, I mean, it's both. It's the fact that they're literally touching the air. So they have very good feedback.
Right. Yeah. And they have that little bit of adjustability. I think was it ducks, or there's some bird that can actually adjust the pinions of its feathers in order to be a little bit more adaptive. And yeah, I think NASA's been doing some of that stuff about a little bit more adaptability and controllability of the aircraft in real time, where you actually change the aspect ratios and other parameters.
So Ra asked the question of, do you recommend any textbooks for military and passenger airplane aerodynamics and space vehicles?
Oh, yeah, I'm sure. I'm blanking on the one I used in school, but there's a number out there.
It's a really great way to learn to work for ATA.
Yeah.
Okay, so should we?
Gary, I have a question too.
Sure, go ahead.
Yeah, actually, I've been thinking about asking this for a long time because a few years ago, we also have another glider talk. It's a DG-1000. why did your company pick up Perlin instead of DG1000? And are these two the major players in kind of high performance gliders? And actually, Joshua mentioned another company.
Well, that one's defunct. So yeah,
okay.
I touched the Solara 50 back in the day, but they had some gust problems. And then, you know, like now there's Sky Dweller, which I haven't really touched, but they're out of Spain. But now they're setting up domestically, so something's happening there. And I can't remember. There's another pool of money out of the Bay Area. I mean, there's always a pool of money out of the Bay Area. Essentially, you know, another pseudo satellite. So I'm kind of curious to see when it'll resurge, essentially, because we've had enough development in solar panels and batteries that, I mean, if we're willing to let the thing catch on fire, that we could try again.
Yeah. I mean, for us, it was just I mean, we're an engineering services consulting company, so they just reached out to us, said, hey, can you help us in this area? And originally it was just to be a very small piece of the puzzle. And then as it went along, we just sort of kept on going, hey, have you thought about this? Have you thought about this? And ended up obviously becoming a much more intensive project. But yeah, we have we get to, because of the nature of our work, we really test anything that vibrates. So you can do a lot of really fun both aerospace and non-aerospace applications.
I do note that you mentioned you have Shaker in your company, so that's also good for testing satellite.
Yep.
You know.
Oh, yeah, Zephyr is the name I was thinking of. There's a new one out of Berkeley that's called Zephyr.
Zephyr.
Yep.
Yeah. Okay. Yeah. So I see. So what I mean is, Perlin approached you initially a small vibration problem, then you expanded to a full scale. So what happens if this people doing this DG1000, they approach you, you can still also do something analysis for them. That's what you're saying, if they contact you.
Yeah, I mean, I would go back to our contracts people and make sure that we didn't have any agreements, but yeah, generally, as long as you're not providing proprietary or competitive advantage information.
I see. But are they competing each other, the DG1000 and Perlin?
Okay,
that's business.
Yeah, I don't know about that.
So I've usually used ATA for space applications. How big is the aeronautics side of the company?
So we don't really, what's the word? We differentiate based on field, but not on application. So
okay.
So I guess I would say our aerospace and our aero and our space are both the size of our company. It's just we have people who do thermal, who do structural, who do acoustics. But yeah, as long as you have money, we're willing to help you.
All right.
True consultant.
Yeah.
But it's also very important to get, like Microsoft, you get people to use it, get used to it, and more people buying it. So we are doing also kind of outreach education here. Do you have some kind of nonprofit version or kind of a demo version, when we do outreach? And we actually also plan, we can work on some AIAA Los Angeles workshop, and then you can come here that we can do. But do you have also something like like a cheaper or free version? When you do outreach, you can show the kids or the kids get familiar with your service and product.
I think if I heard you correctly, you're saying
of course those center, the Siemens probably have contract, but you also mentioned about something virtual pilot. The virtual control room, virtual pilot, some kind of interesting product.
Yeah, so that's not ours. The virtual cockpit is actually Perlin's. They created basically a way for anyone online who wants to track their flights in near real time. They have a website where you can actually watch it and you can see the different flight parameters.
So that wasn't powered by Tesla. It was totally separate.
Yeah, correct. That was a basically it's just a they took their telemetry data and streamed it to just a front end visualization that you could really just kind of follow along with them.
Yeah. Okay.
But yeah, I mean, in terms of, I guess, encouraging the next generation and so forth, I mean, we're always trying to present at schools, free webinars. I mean, I'm sure like you guys are just always trying to encourage interest in education.
Yeah,
Absolutely. And so on the hardware and software side, Siemens definitely does have programs for academia. So if it's for academic use, university licenses,
okay.
those can be down to complimentary for both test and simulation. So for test lab and sim center.
Okay.
Let me go back to another question that was right in here in the chat. And any references for first order wing weight buildup models that take desired flutter characteristics into account before going to the fan?
I'm sure there are. Nothing off the top of my head.
While you're thinking about that, my first order answer to that is that the aircraft design generally are established by the requirements and the functionality of the surfaces. And so when you need a high aspect ratio wing, that's what you go for. You make it as thin and light as you can, and within the strength and performance requirements. And then you find out what you got as a flutter characteristic. And then you subsequently come in and modify things if necessary. But no, you can't guess these things. The FEM is what gets you the answer.
Yeah, I think I agree with that.
And they're not necessarily thin. Sorry.
No, go ahead.
Yeah, I was going to say, and always think when you have high aspect ratio vehicles that at the armpit, the wing airfoil is probably not that thin. If you look at like the Predator, I mean, those cord thicknesses are 40, 50%. I mean, they're pretty fat wings.
Mm-hmm.
See that.
Structures guys like that.
Makes our life easy. Yeah.
Yeah, I don't
Big torque box, tall. Yes.
Let me see if you can see.
The structures book that I used in college by Brune shows an image, a cartoon that was shown by, it was drawn by the various goals of the various disciplines. And of course, the engine the power plant people want big engines, and the aircraft, the structures guys want
I-beam.
straight structures with I-beams and minimal thicknesses, and the aerodynamicists so each discipline has their own ideal configuration, and any aircraft is the consequence of compromise between all those groups.
Right. Yeah. Plus, you forgot the sales and marketing people who have to convince people to buy it.
Make it sexy.
Yep.
Right.
That's where the spaceship comes in.
All right. I don't see any more questions.
We did a very nice and complete job of this. We're getting a lot of congratulations about the wonderful presentation. I fully agree.
Great. Well, thank you, everyone. And thank you, Gary and Ken and the whole AIAA community for inviting us. And yeah, please reach out if you have additional questions, comments, or
you want to buy something.
Yes.
Yes. All right. Well.
Yeah.
All right. Thank you, Tim. Thank you, Gary.
Thank you, everyone.
Thank you.
Thanks, guys. Have a good weekend.
Okay. I guess we can stop the recording at this point.